For years, rumors about the most advanced hypersonic jet have bounced around defense forums and classified briefings. Now the wait is over. The United States has revealed some of the capabilities of the SR-72 Darkstar, and the technology is out of this world. The Darkstar doesn't just fly fast, it rewrites the rules of modern warfare, sending a strong message to rivals like China and Russia that the United States remains unbeatable in hypersonic dominance. What capabilities of the SR-72 are still classified? And is this the aircraft that would make existing defense systems obsolete overnight? Join us as we uncover the capabilities of the SR-72 Darkstar, the hypersonic jet set to change air power forever. Rumors of this mysterious new aircraft have been going around in aviation and defense circles for years. And now the United States has finally unveiled its very own Darkstar, the most sophisticated spy plane ever developed. It is hypersonic, which means it can travel more than 5 times the speed of sound. This news has ended about 10 years of speculation regarding what's being developed behind closed doors. Rolling out the SR-72 sends a clear message to everyone watching. America is not messing around when it comes to next-level military technology. The original SR-71 was instrumental during the Cold War, showing the world what American engineering could pull off. Now the SR-72 is doing the same thing all over again. The Darkstar did not materialize out of thin air. The idea for the jet came about after the retirement of the SR-71 Blackbird in 1999. This jet was so fast that it could penetrate enemy territory without being caught or shot down. However, as times changed, the need to improve the capabilities of the jet became greater, so the United States needed to create something faster, stealthier, and more versatile, and this time they wanted it unmanned to save human pilots on dangerous missions. The problem was obvious. China and Russia have been pouring resources into hypersonic weapons, cranking out missiles and aircraft that fly at increasingly high speeds. These jets could potentially blow right past current defense systems like they weren't even there. Observing the current trends, America needed something to level the playing field as fast as possible. That was what brought about the concept of the SR-72. It was basically designed to be the ultimate spy in the sky. According to reports, the jet is built to slip deep into enemy territory, gather whatever intel it needs, and get out before anyone even realizes something flew overhead. Keeping this program under wraps was incredibly tough. China decided to show off their new hypersonic missile, and Russia did not stop talking about their latest fighter jets. The United States, however, decided the best approach was not to disclose the capabilities of the jet they were developing. The strategy they used was simple. They decided to let the competition think they were winning, while secretly building something that would make the best efforts of their competitors look outdated. When a few of the capabilities of the SR-72 finally got revealed, it was better than everything else out there. Back on November 1, 2013, Aviation Week in Space Technology dropped an article about the SR-72's development that basically broke the internet. Public interest was so intense that it actually crashed the magazine's servers from all the traffic. Lockheed Martin officials came forward with plans to build a scaled-down test version that could be flown with or without a pilot. This demonstrator would be about 60 feet long, roughly the same size as an F-22 Raptor, and powered by one full-scale engine designed to hit Mach 6 for several minutes at a time. In February 2018, Orlando Carvalho, who was Executive Vice President of Aeronautics at Lockheed Martin, basically shot down all the reports about the SR-72 being in development. He flat out said no such aircraft had actually been built yet. But he did mention that hypersonic research was pushing weapons development forward, adding that eventually, as that technology matures, it could ultimately enable the development of a reusable vehicle. Prior to this, the company may have referred to it as like an SR-72. But now the terminology of choice is reusable vehicle. Then things got interesting again in November 2018 when Lockheed Martin came back with updated information. They reported that a prototype of the SR-72 was actually scheduled to fly by 2025 and would be designed to launch hypersonic missiles. According to their timeline, the SR-72 could potentially enter active service sometime in the 2030s. So basically, they went from denying it existed to giving concrete timelines for prototype flights and service entry within a few months. This fit into the Air Force's hypersonic roadmap, which targeted getting a hypersonic strike weapon operational by 2020 and a penetrating reconnaissance aircraft by 2030. Lockheed officials admitted they had been talking with government agencies about the project, but had not actually secured funding for either the prototype or the engine development yet. The performance of the SR-72 Darkstar is out of this world. It can exceed Mach 6, which is over 4,600 miles per hour. At that speed, the jet could fly from New York to London in under an hour. In military terms, it means the jet can streak across entire continents before enemy forces even know what hit them. The secret behind the speed is something called a combined cycle engine, and it's pretty wild how it works. At normal speeds, it acts like any regular jet engine. Turbines spin around, compress air, and push the plane forward. But here's where things get interesting. Once the aircraft hits a certain speed threshold, the whole system flips into scramjet mode, which stands for supersonic combustion ramjet. When that happens, air gets sucked through the engine at supersonic speeds, mixes with fuel, and basically explodes instantly. This creates the kind of sustained hypersonic flight that most countries are still trying to figure out. This technology essentially turns the SR-72 into a global problem solver that can hit any location on Earth within hours. If there is a high-value target that needs immediate attention, the jet would be there before defensive systems can power up. Everything changes when reaction times get slashed to almost nothing. Most military strategies bank on having time to spot incoming threats, figure out what's happening, and set up defenses. When an aircraft can move anywhere on the globe in under 3 hours, those old strategies become worthless. The focus shifts from pure speed to striking before the enemy even knows something's headed their way. It's like playing chess when the other person can't see the board. The SR-72 Darkstar isn't just fast, it is almost invincible. The body of the jet is covered with special radar-absorbing materials that make it almost completely invisible to enemy detection systems. Even if it flies directly overhead, their radar operators might not see anything on their screens. But here's the tricky part. When something moves at hypersonic speeds, it generates massive amounts of heat, which makes it easy to spot with infrared sensors. The Darkstar solved this problem with an advanced heat management technology that spreads out and hides its heat signature. Heat-seeking missiles that rely on tracking hot objects suddenly have nothing to lock onto. The jet also has some amazing countermeasures. It can jam radar systems, jumble missiles tracking computers, and protect its own flight controls from hackers. Contemporary military forces are not only facing threats from conventional weapons, but also cyber attacks. So the engineers made the jet to be equipped with a digital defense system that is virtually hack-proof. The SR-72 Darkstar is also a flying spy station that is built specifically for intelligence, surveillance, and reconnaissance missions. The whole point is to see everything that's happening and beam that information back to command centers in real time. Thanks to hypersonic speeds, it can go into hostile territory, take whatever intel is needed, and bounce out before enemy forces even know something flew overhead. It has sophisticated sensor technology capable of capturing ultra-high-resolution pictures of ground troops or the missile launch systems, even if the system is using camouflage technology. And it is not only about taking these pictures. The jet can also intercept and decode enemy radio broadcasts, including their communications. When visual surveillance is combined with electronic wiretapping that delivers in real time, military commanders have a better chance to know who fired on whom and why, rather than just guessing from incomplete facts. The Darkstar operates as part of a bigger network, linking up with satellites to cover way more ground. All the data it collects during a mission gets beamed straight up to satellites orbiting overhead, which then pump everything into AI-powered analysis systems. The jet is not just about intel gathering. The SR-72 can perform in another capacity, serving as a battlefield coordinator to tell drones, bombers, and naval strike teams by directing them on exactly where to hit. The Darkstar is fast and stealthy, so it has enough bandwidth for all the sensors that it carries. When it comes to modern warfare, the tracking system on the jet is also second to none. Having real-time situational awareness could very well spell the difference between mission success and outright failure. Reports have it that the SR-72 is loaded with next-generation missiles. But here is where it gets really scary. When the missiles get launched from a platform that's already moving at Mach 6, they sometimes miss, and missing targets at that speed can be catastrophic. This is where the jet really shines. The target on the aircraft is spot on, and it hardly ever misses. Compared to current air-based long-range bombers and missile systems, the SR-72 strike is in a class of its own. Bombers like the B-2 Spirit or B-21 Raider are stealthy, yes, but also subsonic, which suggests they take hours just to get to their targets. The Darkstar totally turns that idea on its head. It can hit from anywhere on Earth in 10 minutes. It is in many ways a reimagination of extreme speed. Therefore, it is not just fast, it is smart. It is designed with a semi-autonomous system that can think critically and make decisions in split seconds. At the heart of this ability is an advanced artificial intelligence. This AI can manage flight control, analyze threats, and plan mission routes in real time. This is what makes the jet 10 times better than other jets in its class. At supersonic speeds, it can assess risk and change flight paths in the split second that it would take a human pilot to react to an incoming attack. This digital brain system gives the SR-72 a huge advantage when things get intense at hypersonic speeds. Whether it's dodging incoming interceptors, reacting to surprise missile attacks, or spotting a target that only appears for a few seconds, the AI keeps the aircraft ahead of whatever's happening. The ability to instantly crunch data from dozens of different sensors means it can make lightning-fast decisions that no human pilot could ever handle on their own. When everything's happening at Mach 6 speeds, there's literally no time, so the AI has to take over and make calls in milliseconds. That could mean the difference between mission success and getting shot down. News about the SR-72 Darkstar has basically shaken up defense circles around the world. American allies like NATO countries, Australia, and Japan are already asking questions about how this aircraft might fit into joint military operations. For nations that already work together on intelligence sharing and quick response missions, the Darkstar represents a massive upgrade. The ability to gather intel or launch precision strikes in minutes instead of hours. This could seriously boost Allied deterrence power, especially in hot zones where making fast decisions can be the difference between stopping a conflict before it starts and watching things spiral out of control. Military planners in allied nations are probably scrambling to figure out how to incorporate this kind of capability into their existing strategies. Meanwhile, on the flip side, rival nations are going into overdrive mode. China and Russia have already dumped tons of money into hypersonic research, but seeing the Darkstar officially revealed might push them to hit the gas pedal even harder on their own programs. Security experts are getting worried that this could kick off a whole new kind of arms race, one where being fast and invincible matters more than having big, tough equipment. Instead of building massive tanks or huge bombers, countries are now racing to see who can build the fastest, stealthiest aircraft that can strike without warning. Some analysts think this shift towards speed and surprise attacks could make the world a more dangerous place, since traditional deterrent strategies might not work when weapons can appear out of nowhere in minutes. Defense experts are starting to sound alarm bells about what this could mean for global stability. If the Darkstar really does give America the power to hit any target on Earth with almost no warning time, other countries are going to feel massive pressure to build their own countermeasures. That means more advanced anti-satellite weapons, hypersonic interceptors, and probably technology nobody's even thought of yet. The problem is that when military technology takes these kinds of huge leaps forward, it usually creates unpredictable ripple effects that mess with the balance of power. History shows that these sudden jumps in weapons capability often lead to situations where nobody really knows how the new rules work, and that uncertainty can make things way more dangerous than before. What makes this even more interesting is everything the Pentagon isn't talking about. Sure, they have shared details about the Darkstar's speed, stealth tech, and spy capabilities, but rumors keep floating around about way more advanced capabilities that are still classified. Some people are talking about next-generation laser weapons and electronic warfare systems that could shut down enemy defenses without even firing traditional weapons. There are conversations about secret tests involving space-based technology that nobody's supposed to know about. If any of these rumors turn out to be real, then everything the public has seen so far might just be scratching the surface. The military could be sitting on capabilities that make the already insane specifications of this aircraft look tame by comparison. The SR-72 Darkstar is not just a technological breakthrough, it is also one of the priciest aerospace projects America has ever tackled. Development costs are estimated somewhere in the tens of billions range, and production numbers are going to be pretty limited in the beginning. The Pentagon is basically trying to figure out how to justify this massive price tag, while other huge defense projects like new submarines and next-gen fighters are all fighting for the same funding. Lockheed Martin has put together a manufacturing strategy that can work both ways, either small batches for specialized missions or scaling up to bigger numbers if Congress decides to open the checkbook wider. The timeline has the first combat-ready Darkstars rolling out somewhere between 5 and 7 years from now. Early deployment will probably happen at major Air Force bases, and there's talk about integrating some of these aircraft into carrier strike groups so they can operate anywhere around the globe. It's a massive investment, but the military seems convinced that having this kind of capability is worth the astronomical cost. Once in service, the SR-72's earliest missions could include deep reconnaissance over contested regions, deterrence patrols to project American power, and precision strikes on high-value targets. This will require specialized training for both operators and support teams, given the aircraft's unmatched speed, advanced systems, and semi-autonomous capabilities. The United States Air Force is reportedly preparing simulation programs and joint exercises to ensure crews can handle missions that might unfold at hypersonic speeds, where decisions must be made in seconds rather than minutes. Outside of military circles, the Darkstar has become a massive cultural phenomenon, especially after the fictional version in Top Gun: Maverick. Aviation enthusiasts have been obsessing over whether the jet actually existed for years, while conspiracy theorists have been cooking up wild stories about secret test flights over Nevada and connections to classified space programs. Since the official reveal, media outlets have been covering the story nonstop, and honestly, it's working out pretty well for the military. All the hype is getting people excited about joining the Air Force and building public support for these expensive defense programs. When something looks this cool in movies and gets this much attention online, it makes the whole military tech scene seem way more appealing to potential recruits. The Pentagon probably didn't plan for this, but they're definitely not complaining about all the free publicity. Looking down the road, the SR-72 might just be the opening act. Defense insiders are dropping hints about possible follow-up aircraft, like an SR-73 or maybe even a hypersonic spaceplane that could actually reach low Earth orbit. Improvements in engine tech, heat-resistant materials, and AI flight controls could eventually merge hypersonic aircraft with orbital platforms, creating machines that can switch between flying in the atmosphere and operating in space without missing a beat. The rollout of the SR-72 isn't just another military achievement. It's basically kicking off a whole new chapter in aerospace technology. This is the start of an era where speed, stealth, and the ability to reach space all get combined into one package, completely changing what it means to dominate airspace. Instead of just controlling the skies, future aircraft might control everything from ground level all the way up to orbit. It's like the difference between owning a car and owning a car that can also turn into a rocket ship. Stealth is back, and the world is watching. Recently, news about the US reactivating its legendary F-117 Nighthawk has fueled speculation that a next-generation stealth platform, possibly the Darkstar, is in testing. Russia and China, both racing to advance their own stealth capabilities, are on high alert. The return of the Nighthawk isn't just about nostalgia, it signals America's continued dominance in stealth warfare. Is the Nighthawk truly back? If yes, why bring it back now? Join us as we explore the capabilities of the United States F-117, which has terrified Russia and China. Two F-117 Nighthawks flew low over Baghdad, staying beneath the clouds to avoid detection. On the ground, radar-guided missile systems scanned the sky, searching for enemy aircraft. But the stealth jets barely registered, appearing as nothing more than faint blips that blended into background noise. Their mission was clear: strike a high-value target without being seen. As the bomb bay doors opened, 2 GPS-guided bombs dropped toward a suspected hideout of Iraqi President Saddam Hussein. But opening the bay doors could expose the aircraft to enemy radar. With their position potentially compromised, the pilots quickly turned and exited hostile airspace before the enemy could react. The F-117 was built for precision strikes, not dogfights. It had no defensive weapons and was slower than most fighter jets. Its survival depended entirely on its ability to remain undetected. During the Gulf War, the F-117 successfully struck 1,600 high-value targets without a single aircraft lost. The F-117's development was a gamble on radical technology. Engineers at Lockheed's Skunk Works designed an unconventional aircraft based on stealth rather than aerodynamics. Its sharp-angled, faceted shape, called the hopeless diamond, was meant to scatter radar waves, making it nearly invisible. But experts doubted it could fly. Even Kelly Johnson, the legendary Skunk Works leader, was skeptical. Despite the doubts, Ben Rich and his team refined the design. Using a translated Russian scientific paper on radar reflections, they calculated the ideal shape for avoiding detection. Engineers made precise adjustments to ensure the aircraft could fly while maintaining its stealth properties. The result was the world's first operational stealth fighter, a plane that could strike deep into enemy territory without being seen. Military technology is a constant battle of adaptation. Before stealth, high-speed jets dominated air combat. But as radar and missile technology improved, traditional aircraft became easier to track and destroy. The F-117 changed the equation. Instead of speed or firepower, it relied on invisibility. It wasn't designed to win in a direct fight. It was built to strike before the enemy even knew it was there. From the Gulf War to Kosovo, the F-117 proved that stealth was the future of warfare. Though it was eventually retired and replaced by more advanced aircraft like the F-22 Raptor and F-35 Lightning II, its impact remains. The Nighthawk didn't just change how wars were fought, it reshaped the future of military aviation. In 1973, something shocking happened in the Yom Kippur War, a wake-up call that the U.S. never saw coming. Israeli pilots, flying some of the best American-made fighter jets, suddenly found themselves dropping out of the sky at an alarming rate. In just 18 days, 109 aircraft were lost. But these weren't just dogfights between jets. Most of the planes were blown out of the air by Soviet-made surface-to-air missiles supplied to Egypt and Syria. These Soviet missile systems were a game-changer. Unlike fighter pilots, who needed years of training, SAM crews could be trained quickly and operate at a fraction of the cost. The missiles were devastatingly effective, and the sheer numbers made them nearly impossible to dodge. The Soviets had spent billions developing radar-guided missiles, and their power was terrifying. Take the SA-5 missile, for example. It could soar to 125,000 feet. That's higher than most planes could ever fly, and even carry a nuclear warhead. Imagine an American bomber flying into enemy airspace, only to be met with a missile that explodes with the force of a nuclear blast. Even worse, if these warheads were used, the shock waves wouldn't even reach the ground. Instead, the wind would carry the radioactive fallout straight into Western Europe. This wasn't just theory. The battlefield had changed overnight. Military planners did the math, and the results were horrifying. If a full-scale war broke out between the US and the Soviet Union, the entire US Air Force could be wiped out in just 17 days. The Cold War balance had suddenly tipped in favor of the Soviets. Faced with total air dominance by Soviet missiles, US military planners scrambled to find a solution. Two major strategies emerged. The first was to fly as low as possible, hugging the terrain to stay hidden from the radar. If radar couldn't detect a plane flying just above the ground, pilots could avoid missiles altogether. This thinking led to the creation of the B-1 Lancer, a bomber designed to fly at extremely low altitudes. Its swing-wing design lets it fly slow and steady near the ground, but also speed up and climb high when needed. While low-altitude flight was promising, another idea was about to change aviation forever. Enter Dennis Overholzer, a scientist at Lockheed's top-secret Skunk Works division. He dropped a thick stack of papers on the desk of Ben Rich, his boss, And inside that document was something extraordinary, a formula that could predict how radar waves bounce off different shapes. With a hopeless diamond as a foundation, Skunkworks engineers faced a massive challenge, turning a radar-evading shape into a real aircraft. Stealth was the priority, but the planes still had to fly, carry weapons, and complete missions. Every decision had to balance invisibility with functionality. First, the mission profile was set. The F-117 wouldn't be a dogfighter or a high-speed interceptor. It would be a precision bomber designed to sneak past enemy defenses and strike high-value targets with pinpoint accuracy. To remain undetectable, it couldn't carry external weapons. Instead, it would house its bombs inside 2 internal bays, hiding them from radar. This design limited its payload capacity, but stealth mattered more than firepower. One major problem? The F-117's unique shape made it aerodynamically unstable. Traditional planes have smooth, curved surfaces that help them glide through the air efficiently. The F-117, on the other hand, had sharp angles and flat panels designed to scatter radar waves. This made flying it incredibly difficult. It simply wasn't built to stay in the air on its own. The solution? Fly-by-wire technology. Instead of relying on a pilot's instincts alone, the F-117 had an advanced computer system that made constant adjustments to keep the plane stable. Without this system, the aircraft would be nearly impossible to control. The Nighthawk's engines had to be hidden to reduce its infrared signature, making it harder for heat-seeking missiles to lock on. Engineers buried the engines deep inside the fuselage and used special exhaust vents to cool the hot air before it left the plane. This design reduced heat emissions and limited speed. The F-17 wasn't fast like a fighter jet. It had to rely entirely on stealth, avoiding enemy threats rather than outrunning them. Another trade-off was maneuverability. The F-117 wasn't built for sharp turns or aerial dogfights. It didn't have afterburners, and its unusual shape made high-speed combat nearly impossible. But these sacrifices were worth it. The plane could enter enemy airspace, drop precision bombs, and escape without being detected. After years of secret development, the F-117 was finally ready for real-world missions. It made its combat debut in 1989 during Operation Just Cause in Panama. But its true moment of glory came in 1991 during the Gulf War. The Nighthawk led the first wave of airstrikes, slipping past Iraq's powerful air defenses and destroying key targets with laser-guided bombs. Despite flying deep into enemy territory, not a single F-117 was shot down. It proved that stealth technology could change the rules of warfare. You couldn't shoot what you couldn't see. The success of the F-117 paved the way for modern stealth aircraft like the F-22 Raptor and F-35 Lightning II. Though officially retired in 2008, the Nighthawk's legacy lives on. And now, with reports of it flying again, the question remains: is the U.S. testing something even more advanced? The F-117's main weapon was laser-guided bombs. Inside the nose, it had a moving turret with an infrared sensor that could zoom in and out. A second infrared sensor sat next to the front landing gear. Both sensors had lasers that could lock onto a target and guide bombs with extreme accuracy. The sensors worked with the plane's internal navigation system, switching between forward and downward views to track targets as the aircraft flew over them. However, these systems relied heavily on clear weather. Clouds could block the laser guidance. To solve this, the F-117 could also use GPS-guided bombs. Despite its advanced targeting system, the F-117 had no defensive weapons. It was completely unarmed against enemy aircraft, relying only on stealth to avoid detection. Because of this, it was designed as a subsonic plane, meaning it stayed below the speed of sound. A sonic boom would give away its position, not to radar, but to anyone nearby. Moving at high speeds also caused more friction, heating up the plane's surface, which could make it easier to detect with infrared-guided missiles. To keep the aircraft hidden, engineers chose not to use afterburners or complex engine inlets. Instead, they equipped it with General Electric J85 engines for the early test version and later upgraded to the F404 engine from the FA-18 Hornet. These engines were cost-effective, reliable, and easy to maintain. The engine air inlets were another unique feature. Normally, radar waves can bounce around inside an inlet, similar to how sound echoes inside a cave. The F-117's inlets were covered with a special radar reflecting grid to prevent this. This grid had tiny gaps, each just 1.5 centimeters wide. These gaps were small enough to block most radar waves from passing through. Any waves that did get through would hit radar-absorbing material inside the inlet, reducing the plane's radar signature. The entire aircraft was coated in RAM to absorb enemy radar signals. However, covering the inlets created a major challenge. It reduced the air pressure going into the engine. Normally, an engine inlet is designed to maximize airflow and maintain high pressure for peak performance. The mesh covering the F-117's inlets blocked some of that airflow, which reduced engine power. To fix this, engineers added secondary air intake doors that could open at lower power settings to increase airflow. These doors opened automatically when the plane flew below Mach 0.5 and gradually closed as it picked up speed. They also served as an access point for maintenance since the main intakes were covered. Another big issue was ice buildup. Aircraft flying at high altitudes can collect ice, which can block sensors and reduce performance. Small parts, like airspeed sensors, usually have built-in heaters and drains to prevent this. But the F-117's inlet grid was too large for standard heating elements. Instead, engineers installed an anti-icing system that sprayed a glycol-based de-icing fluid. A small wiper extended from below the inlet to spread the fluid and keep the grid clear, ensuring the engines got enough airflow. The next step was shaping the engine's exhaust outlet. The F-117 had a very unusual design because engineers wanted to reduce both its heat and radar signatures. To do this, they needed to cool the exhaust quickly and spread it out over a larger area to blend with the outside air faster. Instead of a simple round exhaust, the design transitioned into a long, flat rectangular shape with a 17-to-1 ratio. To further control the heat, the outlet was split into smaller channels. Below the exhaust, the fuselage extended outward at a slight upward angle, forming what was called the platypus tail. This special design spreads out the hot air, allowing it to mix with cooler air more effectively. On top of that, the extension was lined with heat-absorbing ceramic tiles that were constantly cooled by bypass air flowing around the engine. However, this unique exhaust system led to unexpected instability during the half-blue test flights. The thrust from the engines was directed slightly inward toward the plane's center line, but this angle wasn't always perfectly balanced. Depending on speed, engine power, and angle of attack, the thrust angles could differ by as much as 8 degrees, pushing the plane sideways. One major issue was something called side slip. This happens when the wind hitting the aircraft doesn't match the direction it's moving, something common during takeoff and landing, especially in crosswinds. The F-117's flight computer used an accelerometer to measure side slip, but the uneven thrust from the engines made the aircraft drift slightly. The computer thought this was a real side slip and tried to correct it, but in doing so, it actually created real side slip, making the situation worse. This started a feedback loop where the plane kept overcorrecting itself. To fix this, engineers introduced a more reliable way to measure side slip using a beta vane, a small device that detects airflow direction. In aviation, beta is the technical term for side slip, and this new system helped the flight computer make accurate adjustments. With the engine and exhaust system set, the next challenge was designing the wings. Engineers had to consider many factors, such as the wing's angle, shape, and size. Normally, designers can adjust these elements based on what the plane is meant to do. For example, an airliner's wings are designed for fuel efficiency at cruising altitude, while a fighter jet like the F-16 focuses on agility and high-speed turns. But the F-117's engineers had limited options. One of the biggest restrictions was the wing's sweep angle, which refers to how far back the wings are angled. This angle is usually determined by the aircraft's speed. Small planes like Cessnas don't need swept-back wings because they fly at slow speeds. Airliners, on the other hand, have angled wings to reduce drag and fly faster before running into issues with shock waves caused by near-supersonic speeds. For the F-117, stealth was the top priority, meaning its wing shape had to fit into the overall stealth design, rather than be optimized for performance like a traditional fighter jet. The Boeing 787 has wings that sweep back at an angle of 32 degrees. Supersonic jets, like fighter planes, also have swept-back wings, but their angles depend on speed. The reason is to prevent shock waves from hitting the wings, which would create too much drag and reduce lift. For example, the F-16 has a sweep angle of 40 degrees, while even the super-fast SR-71 Blackbird only has a 53-degree sweep. The experimental HAB-Blue aircraft had an extreme sweep of 72 degrees. The F-117 Nighthawk, however, wasn't designed for speed. It was supposed to fly at subsonic speeds, similar to a passenger jet, so that a 32-degree sweep would have been enough. But the F-117 needed to be invisible to radar, and stealth design forced engineers to push the wing sweep far beyond normal limits. This choice led to some tough challenges. Swept wings naturally generate less lift than straight wings of the same size. The problem was worsened because the F-117's wings couldn't have smooth curved airfoils. Instead, its wings were built from flat faceted surfaces, made of 2 or 3 flat panels on top and 2 below. To compensate for this, the F-117 needed extra large wings, 72 square meters. That's a huge wing area for such a lightweight aircraft. For comparison, the F-15 Eagle was designed for agility with a low wing loading. Yet the F-15 had smaller wings and a higher maximum takeoff weight than the F-117. The Eagle's more efficient wing design generated more lift with less surface area. Stealth design forced engineers to make other compromises too. The HAB-Blue test plane originally had a platypus tail extension that acted as a flight control surface. If the plane's angle of attack, that is, how much the nose pointed upward, went over 13 degrees, the tail would automatically move downward. But this system malfunctioned just 1 meter above the runway during a test flight. The plane slammed into the ground, bent its landing gear, and forced the pilot to eject. After that disaster, the platypus tail was removed from the final F-117 design. Another issue came from the way the plane was controlled. Unlike normal fighter jets with vertical tails, the F-117 had V-shaped tail fins that could move in different ways. If the fins moved opposite each other, they helped the plane turn. If they moved together, they controlled the nose's up and down movement. However, during steep climbs, the plane's fuselage blocked airflow to these fins, making them less effective. Engineers had to make adjustments to improve stability. The F-117's long-range missions added another challenge. To reach Saudi Arabia for Operation Desert Storm, these stealth jets had to fly for 15 hours and refuel 7 times mid-air. Their refueling system was built into the top of the fuselage and could rotate into position. But because the F-117 had poor low-speed handling, it wasn't suited for aircraft carriers. Lockheed once proposed a carrier-based version, the F-17N, which would have included a tailhook and bigger wings for better control. However, this idea never took off. Despite its quirks, the F-117 performed incredibly well in combat. During Desert Storm, 36 of these stealth jets operated from Saudi Arabia, hitting high-value targets deep in enemy airspace. On the first night alone, they struck 26 critical sites, including enemy air defense systems. Normally, such missions would require bombers, fighter escorts, electronic jammers, and refueling tankers, all at a huge cost. But the F-117 did the job with just a few refuelers for support. However, the Air Force knew that stealth wouldn't remain unbeatable forever. Once enemies become aware of stealth technology, they develop new ways to detect and counter it. The golden age of radar invisibility was destined to be short-lived, pushing military aviation into a new era of stealth evolution. The legendary B-2 Spirit stealth bomber has returned with groundbreaking upgrades that push the limits of military technology. Once a Cold War secret, it's now been transformed into a weapon that feels decades ahead of its time. From hypersonic readiness to futuristic invisibility, this aircraft has left rival nations scrambling to catch up. Why are experts calling it the most advanced bomber in history? And what does its rebirth mean for the future of global defense? Join us as we uncover the secrets behind the upgraded B-2 Spirit. The B-2 Spirit stealth bomber has just received a round of upgrades that defense analysts describe as almost unbelievable for an aircraft that first flew more than 3 decades ago. What was once a Cold War marvel has now been reshaped into something that feels designed for the next generation of warfare. At the heart of this modernization effort is a system called Spirit Realm 1, or SR-1. With this open mission system setup, the bomber can take on new weapons and functions through simple software updates instead of requiring costly hardware changes. Thanks to this framework, the Air Force can integrate advanced munitions, such as the GBU-72 bunker buster, and may even prepare the platform to carry hypersonic missiles, all without dismantling the aircraft. Engineers took a very different approach with this upgrade. By adopting what they refer to as a software factory model, teams are now able to design, test, and roll out new features at a speed that would have been unimaginable in the past. This method reduces defects, speeds up development, and ensures that the new features work seamlessly alongside the B-2's existing avionics. The cockpit has been updated as well. Pilots now work with improved displays that provide real-time battlefield information, helping them plan missions more efficiently and react faster while in the air. Communication systems have been modernized as well, replacing the old single-channel setup with a system that supports simultaneous voice and data transmission. One of the most critical improvements came from advances in satellite communications. Through beyond line-of-sight connectivity, crews are now able to get real-time updates on targets and shifting mission requirements, even when operating deep inside contested airspace. This level of in-flight adaptability greatly improves overall mission flexibility. At the same time, stealth remains the B-2's defining advantage, and engineers have continued working to make it even more effective. A specialized survivability team has introduced both hardware and software enhancements to sharpen the bomber's radar cross-section signature. These tools give pilots the ability to detect, locate, and classify enemy air defense systems while still preserving their low-visibility profile. This round of changes builds on earlier efforts under the Defensive Management System Modernization Program, which upgraded the aircraft's electronic warfare suite. The B-2 can now detect and classify threats while also gathering valuable electronic intelligence, all while remaining cloaked from radar. The timing of these developments is no accident. Both Russia and China have spent years designing advanced radar networks and missile systems specifically aimed at countering stealth technology. Keeping the B-2 ahead of those capabilities is vital, especially since the aircraft continues to serve as America's only long-range penetrating strike bomber. Today, just 19 B-2s remain in service after the loss of 2 aircraft in earlier incidents. Each one undergoes a full overhaul roughly every 9 years, which includes structural maintenance and the reapplication of radar-absorbing coatings. Because the fleet is so small, extending the life and relevance of each aircraft is considered essential for maintaining the United States' ability to strike targets anywhere in the world. The B-2 can deliver up to 40,000 pounds of conventional or nuclear weapons and, with aerial refueling, can reach intercontinental targets without detection. Until the new B-21 Raider enters service later this decade, the Spirit remains the backbone of America's deep strike capability. The Spirit Realm 1 program makes sure the bomber doesn't fall behind. By relying on continuous software upgrades rather than major redesigns, the Air Force can keep the B-2 responsive to evolving technologies and threats. Defense officials believe these changes will keep the bomber viable well into the 20s. The flying wing design that once looked decades ahead of its time has now been adapted again, proving that a concept born in the 1980s can still set the standard for next-generation aviation. The most expensive military aircraft ever built has now advanced to a point where it seems to defy the very rules of radar detection. How can a machine larger than half a football field disappear from the most sophisticated surveillance systems in the world? The B-2 Spirit achieves a kind of invisibility that once seemed impossible. Radar operators facing the aircraft often find their screens showing nothing but empty sky. Despite being 69 feet long with a wingspan of 100 to 72 feet, the bomber can appear no larger than a small bird on advanced detection equipment. The foundation of this ability lies in its design. Unlike older bombers that rely on vertical fins and sharp edges, the B-2 was designed as a seamless flying wing. The design of the aircraft forces radar signals to scatter in multiple directions instead of bouncing straight back to enemy stations, which makes the bomber much harder to track. Equally important is the special coating that covers the entire surface. This material absorbs those signals and disperses the energy as heat rather than sending it back to detection systems. Maintaining that protective layer is a constant challenge. Each bomber must be kept in climate-controlled hangars, and about every 9 years, the aircraft goes through a major depot cycle where technicians carefully strip and reapply the coating to preserve its stealth. The process costs millions of dollars per aircraft, but without it, the B-2 would quickly lose the low visibility that makes it so valuable. Even the engines were designed with stealth in mind. 4 General Electric F-118 engines sit hidden within the wing itself. The air intakes use curved ducts that block radar waves from reaching the turbine blades, which would otherwise light up on detection systems. Exhaust nozzles mix hot gases with cooler outside air to cut down on heat emissions, lowering the aircraft's infrared signature. Heat-absorbing tiles, similar to those once used on the space shuttle, line critical areas of the bomber. These prevent heat tracking systems from locking onto the B-2 even when it operates at altitudes above 50,000 feet. Another remarkable feature is its contrail management system. Most high-altitude aircraft leave long vapor trails that give away their position. The B-2 can suppress contrail formation when necessary, erasing this common giveaway during sensitive missions. Stealth systems come together through what pilots call penetration mode, activated by a button marked PEN. Once engaged, this mode synchronizes all of the bomber's stealth technologies to minimize signatures across radar, infrared, and visual detection. Enemy radar crews often report nothing more than background noise when the B-2 is in this state. The idea of a flying wing is not new. Jack Northrop tested the concept with his YB-49 prototype back in 1947, which had the same wingspan as the modern B-2. Even Germany experimented with a similar design during World War II, building the Horten Ho 229, but their version lacked the advanced materials and precision engineering that would make the American design truly practical. The science behind the B-2's stealth owes much to Soviet research. In 1962, Russian physicist Pyotr Ufimtsev released groundbreaking research on the way electromagnetic waves interact with different surfaces. His work was meant as pure science, but American engineers later applied those principles to develop the B-2's unique radar-deflecting shape. What began as a theory in a textbook eventually became the foundation for an aircraft designed to slip past Soviet air defenses. The result was the B-2 Spirit, a bomber that blends geometry, radar-absorbing coatings, hidden engines, and thermal management into a single design. Together, these features make it extraordinarily difficult to detect with conventional tracking methods. For air defense crews, the reality is simple. It is nearly impossible to shoot down something you cannot see, hear, or lock onto. Even with all the advanced stealth technology built into the B-2, the aircraft itself is useless without the right person in the cockpit. But what exactly makes someone qualified to fly America's most secret bomber? Since the B-2 Spirit program began, fewer than 300 pilots have ever been trusted to fly it. That number is shockingly small when you consider the size of the United States Air Force. It is often described as the most selective flying group in military history, with acceptance rates so low that even the Navy SEALs seem easier to get into. Getting selected is about much more than raw flying skills. Each candidate goes through psychological testing that digs far deeper than the usual pilot requirements. Military doctors look at personality traits, stress tolerance, and even how well someone can get along with others. Missions can last close to 2 full days, with 2 people locked inside a tight cockpit. The Air Force cannot risk putting 2 pilots together if there's even a chance they might clash or buckle under pressure. Physical skill is just as important. B-2 pilots must have excellent reflexes and steady hands, especially for tasks like refueling in the air, which requires near-perfect precision. The B-2 doesn't fly like any other plane. It has unusual flying wing aerodynamics that demand special handling skills. Learning to control it means starting almost from scratch, even for experienced pilots. On top of that, the security checks are among the strictest in the military. Candidates face background investigations that cover their personal history, family ties, and even their finances. The government wants to be sure that no one flying the B-2 could be blackmailed or bribed into betraying sensitive secrets. Training is another hurdle. Before touching the actual bomber, pilots spend months inside advanced simulators that recreate every system, warning light, and emergency the plane might face. Instructors throw constant challenges at them: engine failures, electrical problems, combat situations, and even extreme weather. Only those who make quick, smart decisions under stress can move forward. Mission commanders receive extra instruction beyond just flying. They are trained in weapons use, navigation, and electronic countermeasures that protect the bomber from enemy defenses. While the pilot focuses on flying, the commander handles the systems. Success depends on both working seamlessly as a team during missions that can stretch almost 2 days without landing. The B-2's cockpit is designed differently from most military aircraft. Instead of sitting one behind the other, both crew members sit side by side in ejection seats. This makes long flights easier to manage because communication is more natural. However, it also forces pilots to adapt to a wider forward view that feels very different compared to other planes. All B-2 flights operate out of one location, Whiteman Air Force Base in Missouri. The base has specially built hangars that control temperature and humidity to protect the bomber's delicate stealth coating. Pilots often spend weeks at a time training or preparing for missions, which means long stretches away from family. Interestingly, most B-2 pilots only fly a handful of missions each year. The bomber fleet is small, and each aircraft is unique. To stay sharp, pilots rotate between different planes so they remain familiar with how each one handles. For many, flying the B-2 represents the peak of their career. Once they retire from the program, they often don't move on to fly other aircraft because of how specialized the training is. Instead, some stay connected to the bomber community by working as instructors or taking contractor roles that support the program. The limited number of trained pilots poses challenges for the Air Force. Whenever the bombers are needed, commanders must carefully balance mission schedules, rest time, and training requirements. Each pilot represents years of investment and cannot be replaced quickly. It is this scarcity, along with the difficulty of the training, that makes the B-2 community one of the most exclusive groups in the entire United States military. These top pilots showed their true skill in missions that are still studied by military experts today. But here's the question: how could just 2 bombers completely change the way wars are fought from the sky? The B-2 bomber made its combat debut over Kosovo in 1999, and it instantly rewrote the rules of air warfare. 2 bombers flew missions that lasted 31 hours straight, leaving from Whiteman Air Force Base in Missouri, striking their targets in the Balkans, and flying back without stopping anywhere in between. Even though the B-2 made up less than 1% of all combat flights during Operation Allied Force, it destroyed nearly 1/3 of the priority targets in just the first 8 weeks of the conflict. Military leaders had never seen anything like this. Normally, hundreds of planes and multiple waves of attacks were needed to get the same results. The B-2 managed to do in one mission what entire groups of aircraft struggled to accomplish. The bomber named Spirit of America set a record during Operation Enduring Freedom in 2001. It flew the longest combat mission in history, 44 hours non-stop from Missouri to Afghanistan and back. The engines never even shut down during a quick 45-minute crew change, after which the aircraft immediately launched again for another 30-hour flight. In total, it stayed in continuous operation for more than 70 hours. Each B-2 carried up to 40,000 pounds of guided bombs and smart weapons on these missions. These weapons were so accurate that commanders on the ground reported that the B-2 was able to hit high-value targets that other aircraft couldn't touch. Because the missions were so long, refueling in the air was essential. Every 6 hours or so, a KC-135 tanker would meet the bomber high above enemy territory to transfer fuel. Both aircraft had to fly in perfect sync for the transfer to work, making it one of the most delicate parts of the mission. The B-2 quickly became the aircraft trusted to strike first. It opened operations in Iraq, Afghanistan, and Libya by slipping into heavily defended airspace that other aircraft couldn't enter safely. Once the B-2 had destroyed key defenses, other planes could follow. Today, this first strike role is standard military practice. What made the B-2 so valuable was its ability to hit any target in the world within hours of being ordered. It didn't need bases in other countries or staging areas closer to the fight. It could launch straight from the United States and still complete its mission. Its advanced navigation systems meant it could fly and strike accurately in any conditions. Using radar and GPS-guided bombs, it could hit through thick clouds, heavy storms, or complete darkness. Enemies learned that bad weather could no longer protect them. Each mission proved that the billions spent on stealth technology and long-range strike power had been worth it. The B-2 showed it could achieve major objectives while putting very few aircrew at risk and with minimal civilian casualties. Planning these missions was just as demanding as the flights themselves. Crews spent hours studying maps, enemy defenses, weather, and backup targets before even stepping into the cockpit. Sometimes the planning lasted longer than the actual flight. After the missions, reviews showed the same results again and again. The B-2 hit its targets more effectively than traditional bombing campaigns, while needing far fewer aircraft and weapons to do the job. Despite its remarkable record in combat, America's most advanced bomber faces a serious challenge that could weaken national security. The question is simple but troubling. Why are these rare aircraft disappearing one after another? Back in the Cold War years, the United States planned to build 132 B-2 Spirit bombers. Defense companies prepared for huge orders, expecting that the cost per aircraft would drop once production ramped up. The goal was to create a fleet big enough to eventually take the place of the older B-52 bombers. But history shifted. In 1989, the same year the B-2 took its first flight, the Berlin Wall fell. The Soviet Union collapsed soon after, and with it the need for such a large stealth bomber force. Congress slashed the order from over 100 to just 21 planes. That decision made each B-2 incredibly expensive, more than $2 billion apiece. With so few built, every aircraft became almost like a custom project, each with its quirks and demanding upkeep. Since entering service, the fleet has lost 2 bombers. In 2008, the Spirit of Kansas crashed during takeoff in Guam after faulty sensors caused it to lift its nose too sharply. The crew ejected safely, but the aircraft was destroyed, just like that. America lost 4% of its stealth strike power. Another bomber, the Spirit of Washington, caught fire during maintenance at Whiteman Air Force Base in 2010. Workers accidentally set off a blaze that damaged the bomber's delicate structure and stealth coating. The Air Force debated for years whether fixing it was even possible before finally bringing it back to service. In 2022, another B-2 was badly damaged in a fire and written off completely. That incident left only 19 operational bombers, each one now an irreplaceable part of America's long-range strike force. To keep them flying, every B-2 goes through a deep overhaul about once every 9 years. This isn't routine maintenance, it's a complete rebuild. Workers strip off and reapply the radar-absorbing coating, upgrade the electronics, and replace or repair major systems. Each cycle costs hundreds of millions of dollars and takes months before the plane can return to duty. The aircraft are stored in special climate-controlled hangars at Whiteman Air Force Base in Missouri. The stealth coating is so sensitive that both temperature and humidity must stay within strict limits. If exposed to bad weather or stored incorrectly, the coating can break down, making the bomber easier to spot on radar. Building the B-2 in the first place meant inventing new ways of making things. Northrop Grumman developed advanced composite materials, custom tools, and entirely new assembly techniques just for this program. Once the final bomber rolled out, those production lines were shut down. That means no more B-2s can ever be built with the same methods. Looking ahead, the Air Force plans to keep the B-2 in service until the new B-21 Raider is ready in larger numbers. The Raider is designed with modern materials and updated production techniques, and it also draws on lessons learned from the B-2 program. The first B-21 bombers are expected to be combat-ready later in the decade. For now, though, the B-2 remains the only aircraft that can slip past the world's toughest air defenses and strike anywhere on the globe. Losing even one more reduces America's reach and weakens its ability to respond to threats far from home. Thanks for watching. While you are still here, click on the link on your screen to check out another of our videos. See you there. China just shook the skies. Since the unveiling of the White Emperor, comparisons to the US's NGAD and F-22 have sparked intense debate. Analysts are scrutinizing every detail, from speed and stealth to firepower, as the battle lines in the race for air dominance are clearly drawn. How does the White Emperor truly measure up against these American fighters? And could it tip the balance of power in the skies for years to come? Join us as we compare the capabilities of two sixth-generation airfighters that are bound to change the future of aerial warfare. As tensions between Washington and Beijing continue to escalate, the global race to field sixth-generation fighter aircraft has reached a critical stage, with both nations pouring immense resources into developing platforms designed to dominate the skies and achieve strategic air superiority. The U.S. Air Force's Next Generation Air Dominance Program, or NGAD, is projected to set a new standard when it enters service over the next decade, boasting a combination of manned and unmanned systems, cutting-edge stealth, advanced adaptive engines, and integrated sensor networks. On the other hand, the People's Liberation Army Air Force is constructing its own next-generation fighter, dubbed the White Emperor, which was unveiled recently at the Zhuhai Air Show. According to state-run reports, this ambitious platform is intended to operate not only in the atmosphere, but potentially in near space, showing China's push for strategic flexibility and technological prestige. While some of these claims may appear exaggerated, the rapid pace of Beijing's military modernization, combined with its expanding aerospace capabilities, makes the program a serious point of concern for U.S. military planners. Publicly available images and video footage reveal a fighter with large internal missile bays, capable of carrying increased ordnance without compromising stealth, and a delta-shaped aerodynamic design that emphasizes both speed and maneuverability. Analysts, including the Bulgarian military, have noted the platform's carefully engineered pointed nose, smooth body contours, and multi-layered cockpit canopy, all optimized to reduce radar and infrared signatures, signaling the PLAAF's focus on next-generation stealth. The aircraft's design is said to emphasize a low observable profile while maximizing high-speed maneuverability, allowing it to survive and dominate in contested airspace against advanced fifth-generation and future sixth-generation adversaries. Central to its agility are advanced thrust vectoring engines and a restructured fuselage, which theoretically grant the fighter super maneuverability similar to what the F-22 Raptor can achieve. Such extreme directional responsiveness would be essential in high-stakes air-to-air engagements, enabling pilots to evade missiles, counter hostile fighters, and execute precision strikes under conditions where split-second reaction times could determine the outcome of a battle. The fighter is also reportedly designed with an expanded internal weapons bay, capable of carrying a variety of munitions for multiple mission profiles. This flexibility would allow a single aircraft to switch seamlessly between air-to-air combat, air-to-ground strikes, and even near-space operations, giving the People's Liberation Army Air Force a highly adaptable and survivable tool for both traditional and emerging battle domains. Further distinguishing the White Emperor from its predecessors is the inclusion of directed energy weapons, most notably lasers. These systems, integrated into the airframe, are likely intended to provide simultaneous multi-target engagement, allowing the aircraft to neutralize multiple threats in rapid succession. This capability exemplifies next-generation combat thinking, where advanced sensors, stealth, and precision energy weapons work in concert to provide a decisive advantage. According to reports, including analysis from China Arms, test flights of the White Emperor suggest that the platform is not merely theoretical. It has demonstrated the potential to operate across multiple domains. The aircraft is envisioned to engage in air-to-air duels, precision strikes against ground targets, and missions in near-space environments, where conventional fighters cannot operate effectively. The aerodynamic design also plays a critical role in the fighter's performance. Sleek aerodynamic lines reduce drag while improving stealth, and the multi-layered, reflective minimizing cockpit canopy likely shields pilots from detection. Delta-shaped wings and advanced control surfaces further enhance speed, stability, and responsiveness at supersonic velocities, making the aircraft difficult to track, target, or intercept. Internally, avionics, sensors, and weapon systems are integrated into a unified network, allowing real-time data fusion and rapid decision-making during complex missions. This convergence of stealth, propulsion, and energy weapons is intended to produce a fighter capable of operating independently or in concert with unmanned systems, providing both redundancy and force multiplication. Artificial intelligence plays a central role in the White Emperor, elevating it beyond the capabilities of even the most advanced fifth-generation fighters. This next-generation system is said to process vast streams of real-time data, assess incoming threats, and execute tactical maneuvers without requiring constant pilot input. Such an approach opens the door for both semi-autonomous and fully autonomous missions, where the human role could shift from direct control to mission supervision. This is not just theory. A similar capability has already been demonstrated by the United States Air Force with the experimental X-62 Vista, which showcased how artificial intelligence could assume control of a combat jet in live environments. By following this model, the White Emperor may mark the point where autonomy moves from experimental programs into operational fighter platforms. For the pilot, the benefit is transformative. Instead of being overwhelmed with multiple information streams in the chaos of aerial combat, the onboard systems powered by artificial intelligence deliver immediate, actionable intelligence. Threats can be detected, analyzed, and prioritized in fractions of a second, allowing the pilot to respond faster than human reflexes alone would ever permit. In this sense, the human operator becomes the mission director, relying on the jet's artificial intelligence to execute rapid maneuvers, select optimal weapons, and even coordinate with allied aircraft or unmanned systems flying alongside. Such AI-driven situational awareness effectively allows the White Emperor to fight as a central node in a vast digital battle network. The Aviation Industry Corporation of China has clearly positioned this technology not as an optional feature, but as a core design philosophy. The Indian Defense Research Wing underscored this shift, noting that AVIC's design prioritizes artificial intelligence not just for tactical maneuvering, but as an integral component of multi-unit, networked combat. In practice, this means the White Emperor could seamlessly integrate with other fighters, drones, or command and control systems, exchanging data in real time and executing coordinated strikes across multiple domains. It is a concept that mirrors and perhaps seeks to outpace the United States Air Force's vision for its own next-generation air dominance program, where manned and unmanned systems are designed to operate as a single cohesive force. By integrating this level of autonomy, China is signaling its intent to compete not only in the development of stealth, propulsion, and weapons technologies, but also in the field of digital warfare. The White Emperor could potentially reduce the need for continuous human oversight in high-risk missions, sending unmanned or semi-autonomous units deep into contested airspace where survival odds for a pilot would be minimal. This possibility represents both a technological leap and a strategic shift, moving warfare into an era where decisions are increasingly made by machine intelligence guided by human objectives. The White Emperor is built to be far more than a single-purpose aircraft. Its designers envisioned a machine capable of adapting to nearly any role on the battlefield. This fighter is intended for multi-role missions, able to take on air-to-air engagements, air-to-ground strikes, and even operations in what China claims are near-space environments. Embracing this range, it attempts to cover multiple mission types with one highly adaptable platform. Such flexibility reflects China's broader ambition to field aircraft that are not only powerful but also versatile enough to meet unpredictable combat demands. A major reason for this adaptability lies in the White Emperor's modular systems. Unlike older aircraft that require significant modifications for new missions, the White Emperor can be configured quickly for different combat scenarios. This means the jet can transition from conducting deep strike missions to performing air superiority patrols with minimal delay. In practical terms, this versatility allows China's Air Force to deploy fewer aircraft while still maintaining coverage across a wide variety of missions. By reducing logistical strain and increasing readiness, the White Emperor strengthens China's ability to conduct long, sustained campaigns without exhausting its resources. Equally important is the emphasis on maintenance. A VIC designed for White Emperor with low maintenance requirements in mind. Traditional fourth-generation jets often suffer from long downtimes after missions, but the White Emperor promises high availability with minimal turnaround time. For prolonged operations, where every minute matters, this capability ensures the aircraft can stay in the fight longer and return to the skies faster. It is not just about performance during combat, but also about endurance over the course of days, weeks, or even months of deployment. Where the White Emperor truly shows its futuristic intent is in its networked warfare capabilities. The jet is not meant to fight alone. Instead, it is designed to integrate seamlessly into China's future combat networks, linking up with other aircraft, ground units, and even naval forces. Such interconnectivity transforms the jet from a single war machine into a node in a vast, coordinated system. This concept mirrors the approach of Western programs, such as the United States Air Force's collaborative combat aircraft initiatives, where drones and manned jets work in harmony. By being able to communicate in real time, the aircraft expands tactical options on the battlefield. Pilots can receive live data from drones, pass targeting information to ships, or coordinate with ground-based missile systems. The effect is a wider, more unified battlefield picture, enabling swifter decision-making and more precise strikes. The South China Morning Post emphasized this point by noting, "The jet's networked capability allows coordinated actions with diverse units, reinforcing China's bid for air superiority." Artificial intelligence plays a central role in this networked vision. The White Emperor's onboard systems are designed to process massive amounts of data in real time, filtering and prioritizing information for the pilot, or even handling coordination autonomously. When combined with drones and ground units, this creates a combat environment where China's forces can act faster than their opponents, tightening the decision loop in their favor. Taken together, the White Emperor's operational flexibility and networked capabilities highlight China's determination to dominate future battlefields. By merging adaptability, endurance, and interconnectivity, the aircraft is presented as a cornerstone of a larger vision, one where Chinese forces can seamlessly coordinate across air, land, and sea, maintaining the upper hand in complex, high-intensity conflicts. Unlike traditional fighters, the White Emperor is often described as more than an aircraft, standing somewhere between a combat jet and an aerospace vehicle. Its rumored ability to operate at near-space altitudes marks a fundamental shift in how air dominance might be defined in the future. Reports have emphasized that China's defense industry wants to achieve a qualitative leap that challenges existing superiority dynamics. According to the National Interest, the White Emperor series could reshape contested airspace by bolstering China's ability to project power far beyond its borders. If realized, such an aircraft would not merely match foreign developments, but could redefine them, forcing adversaries to prepare for combat environments extending into the stratosphere. Although details remain scarce, particularly in English-language sources, speculation paints a picture of extraordinary performance. The White Emperor is believed to be capable of reaching top speeds near Mach 5, translating to almost 6,000 kilometers per hour and covering operational ranges beyond 4,500 miles. Its ceiling is claimed to extend past 100,000 feet, placing it within near-space territory where traditional air defenses lose much of their effectiveness. These numbers alone, if proven accurate, would mark the White Emperor as a once-in-a-generation leap in aerial engineering, setting it apart not only from fifth-generation fighters like the F-35 or the J-20, but also from projects aimed at the sixth generation. The role of artificial intelligence is perhaps the most revolutionary aspect. Instead of simply assisting the pilot with navigation or weapons targeting, the White Emperor is expected to function with full autonomy when required. Real-time decision-making, data assessment, and threat prioritization could all be handled by onboard algorithms, giving the jet an option to operate as an unmanned system. Such autonomy would not only reduce risk to human pilots, but also allow the aircraft to push beyond human physiological limits, especially in high-speed, high-altitude engagements. In parallel, its weapon loadout, which is rumored to include hypersonic missiles and directed energy lasers, would give it the capability to strike with both overwhelming force and precision. Another significant factor is the promise of minimal maintenance requirements. If China's designers succeed in reducing logistical burdens, the White Emperor would not only be more powerful than many of its rivals, but also more available, spending less time grounded and more time deployed on missions. This would give the PLAAF a considerable operational advantage in a drawn-out conflict, where rapid redeployment and sustained pressure are key. Much like the NGAD fighter, the White Emperor is expected to operate alongside unmanned systems, with loyal wingman drones serving as expendable extensions of the manned aircraft's operational reach. In the NGAD framework, collective combat aircraft, or CCA drones, accompany the main fighter, reducing the need for larger quantities of manned aircraft and lowering program costs while providing unprecedented battlefield flexibility. The projected timeline for China's sixth-generation fighter calls for operational deployment by 2035, which means a functional design must emerge before the end of this decade, placing significant pressure on designers and engineers. The United States, however, appears further along in the program, integrating advanced adaptive engines, AESA radars, and networked sensor fusion to create a versatile and stealthy aerial platform capable of dominating contested airspace. On the 21st of March, 2025, President Trump announced that Boeing had been selected to build the United States Air Force's sixth-generation fighter to meet the NGAD requirement, revealing that the aircraft would be known as the F-47. The previous year had seen dramatic shifts in America's two next-generation air dominance programs. Budget pressures forced a reevaluation of priorities, pausing the source selection process for NGAD. The Air Force was instructed to reconsider not only the capabilities it required from the crewed fighter at the heart of the NGAD system, but also whether such an aircraft remained necessary at all. Simultaneously, the United States Navy's F/A-XX effort, often also called NGAD, received renewed attention, clarifying earlier misconceptions that the program had been halted entirely. New strategic challenges quickly emerged. Potential adversaries, particularly China, sought ways to deny the U.S. and its allies the freedom to conduct operations in their preferred manner. China's response took the form of the Anti-Access Area Denial Strategy, or A2/AD, designed to prevent American forces from entering key operational areas and to limit their freedom of action within those zones. By using long-range air defenses, advanced missiles, hypersonic glide vehicles, and layered detection systems, China aims to push enemy aircraft to more distant bases, complicate refueling and battle management, and disrupt operational tempo. It is important to note that A2/AD does not make airspace impenetrable. Instead, it forces adversaries to operate under constraints, slowing or redirecting their actions and preventing deep strikes. In parallel, China has sought to achieve significant mass in its forces, challenging the numerical advantage the United States once enjoyed. Andrew Hunter, the outgoing acquisition executive for the U.S. Air Force, acknowledged the competitive pressures, noting that China could beat the U.S. to the punch. He added that while the U.S. may eventually possess superior capability, the U.S. certainly has no time to lose. Current American fighters, such as the F-35A, have a combat radius of only 590 nautical miles, or 1,093 kilometers, while the F-22A has an even smaller radius when relying on supercruise. Both aircraft would need to refuel within approximately 500 nautical miles, or 926 kilometers, of their targets, a requirement that places tankers in vulnerable positions, effectively leaving them as sitting ducks under modern A2/AD conditions. This evolving environment demonstrates why NGAD, combined with advanced air refueling and networked operations, is critical. Without such innovations, U.S. and allied air forces would struggle to penetrate adversary defenses, sustain prolonged missions, or maintain the operational freedom necessary to secure decisive air superiority in the decades ahead. The strategic and technological imperatives driving NGAD reflect a profound shift in how aerial warfare will be conducted against peer adversaries. Another uncomfortable reality is that the United States Air Force can barely afford a next-generation air dominance fighter with a unit cost of approximately $300 million within the time frame the aircraft will be required. This is unusual for a service that has historically been the best-funded Air Force in the world. Currently, the U.S. Air Force is prioritizing the two legs of the nuclear triad for which it is responsible, the B-21 A-Raider bomber and the LGM-35A Sentinel, also known as the ground-based strategic deterrent. Both programs consume a massive portion of the budget, and with the Sentinel program's cost nearly doubling to just under $141 billion, there is little room left for an expensive NGAD manned fighter. This budget constraint, rather than any change in threat perception, drives the push to reduce NGAD costs. Ultimately, a high-capability, long-range NGAD core manned fighter is essential, even if it comes at a high cost. Only about 200 units are expected, and none will likely be exported, limiting economies of scale. Proposals for lighter NGAD variants would augment, rather than replace, the main platform. The Air Force has long considered dual versions, one optimized for long-range, heavy payloads in the Indo-Pacific, and another for shorter-range operations in Europe. The vision includes a clean-sheet design with open mission systems capable of rapid software updates, ensuring the NGAD remains a high-end fighter while allowing smaller, lower-cost aircraft to handle day-to-day missions, preserving the core platform for high-intensity operations. Recent reports of China's sixth-generation fighter taking flight sent shockwaves through the aviation world. With no warning, only action, many assumed China had taken the lead. At the same time, the U.S. paused its NGAD program, fueling doubts about its progress. But what seemed like a setback was actually silence before a storm. Now, revelations suggest the NGAD may be up to a decade ahead of China's fighter. What secrets has the U.S. been keeping? What technologies could place it so far ahead? Join us as we explore the capabilities of the U.S. sixth-generation fighter, believed to be a decade ahead of China. The F-22 Raptor has long been the backbone of the U.S. Air Force's air superiority strategy. Designed specifically to dominate enemy airspace, the Raptor is a powerful and fast aircraft, capable of flying at supersonic speeds without afterburners. It was considered so vital to national security that Congress banned its sale to any foreign country. However, despite its impressive capabilities, the Raptor fleet is aging. Introduced in 2005, only 185 F-22s are currently in service, and new challenges are quickly emerging. One of the biggest threats comes from China, which has made major advancements not only in missile technology, but in its sixth-generation air fighter. Long-range attack missiles and advanced surface-to-air systems now pose serious risks to traditional fighter jets. These weapons could potentially strike American aircraft even before they leave the ground, or prevent them from getting close enough to perform their missions. The idea of flying directly into enemy airspace is becoming more dangerous as modern defenses grow stronger and smarter. To keep ahead of these evolving threats, the U.S. Air Force launched the Next Generation Air Dominance program. This project aims to create the world's first sixth-generation fighter jet, one that can replace the F-22 and remain dominant in the skies for decades. NGAD is not just about building a single aircraft. It's about designing a family of systems. At the center will be a large, manned fighter jet, supported by smaller, unmanned drones that can fly alongside it. These drones, often called loyal wingmen, will help carry out dangerous missions, gather intelligence, and even engage enemy targets. The NGAD concept started with a 2014 DARPA study. Over the next decade, the idea evolved into a full-fledged program focused on advanced stealth, speed, sensor fusion, and network warfare. The future of air combat has been the subject of intense debate, especially around whether manned fighter jets still have a place in modern warfare. Some high-profile voices like Elon Musk have suggested that unmanned drones are the future and that the era of piloted aircraft is ending. These ideas sparked uncertainty within the U.S. Air Force, and by late last year, the Next Generation Air Dominance program, a massive effort to build a sixth-generation fighter jet, was quietly placed on indefinite hold. For many, it looked like the traditional fighter jet's days were numbered. Then came a stunning twist. On March 21, in a move that surprised defense experts and industry insiders alike, President Trump abruptly awarded Boeing the contract to build the Air Force's most advanced fighter jet yet. The aircraft would be named the F-47, and it would push forward where NGAD had stalled. What shocked many observers was how early the decision came, before key officials, such as the Secretary of the Air Force and top defense acquisition leaders, had even been confirmed by the new administration. Aviation analyst Bill Sweetman noted that such a bold and early commitment to a major defense program was completely unheard of. Yet the announcement sent a strong message. The U.S. is still betting big on traditional air power. While tech entrepreneurs like Musk advocate for fleets of smaller, cheaper drones, military experts remain cautious. The geography and operational demands of the Pacific region, especially in a potential conflict with China, are very different from those in places like Europe or the Middle East. In those regions, air bases are close to the battlefield. In the Pacific, U.S. aircraft often need to fly long distances across oceanic stretches to reach targets or support allies. This vast distance makes range and endurance key requirements, something small drones struggle to provide. Even the F-35, a state-of-the-art fighter, has a limited combat radius of around 500 miles, which may not be enough in a Pacific conflict. The F-47, by contrast, is expected to offer significantly greater range and speed, ensuring it can operate effectively over the expansive Pacific theater. Sweetman summed it up by saying, "Whatever one's view of the F-22, it can't be replaced by a quadcopter." In other words, advanced drones still can't match the reach, speed, and firepower of a full-size fighter jet in many combat scenarios. The Pacific isn't Ukraine. Small, cheap drones might work in localized European conflicts, but they fall short in long-distance, high-stakes warfare where the U.S. needs to project air dominance over oceans and vast territories. The F-47 represents a clear vote of confidence in the enduring value of manned air power. It signals that, at least for now, the U.S. military isn't ready to give up the cockpit, not when the future of global air superiority still depends on pilots flying cutting-edge machines across the world's largest and most challenging battlegrounds. Shockingly, the U.S. Air Force's next-generation fighter jet will still have a human pilot in the cockpit, a decision that has sparked debate, especially among tech leaders who favor AI-controlled aircraft. Elon Musk, one of the loudest critics, has been vocal about his belief that manned jets are outdated. Back in November, Musk posted on X, his own social media platform, that fighter jets piloted by humans will be destroyed very quickly. He has repeatedly claimed that the future of warfare lies in autonomous drones, not piloted jets, and that the age of the fighter pilot is coming to an end. Despite such predictions, the F-47's manned design reflects a different strategic outlook. Although the U.S. Air Force has not released official specifications yet, open-source information suggests that the jet will be large, powerful, and built for long-range missions. Similar in concept to the legendary F-111 bomber used from the 1960s through the 1990s. Aviation expert Bill Sweetman has pointed out that the discussions surrounding its engine indicate it could be significantly bigger than existing fighters, with enough range to operate deep into enemy territory, particularly in the Pacific. This long-range approach is exactly what some defense experts support. Justin Bronk, a senior research fellow at Royal United Services Institute, agrees with the Air Force's decision to design the F-47 as a large crewed aircraft. In his view, this is especially important in the Indo-Pacific, where the vast distances between U.S. bases and potential combat zones require aircraft that can fly far without refueling. A small drone simply wouldn't do the job. Bronk also highlights a crucial limitation of AI in warfare: its inability to operate independently when communication systems fail. In real-world combat, radio links can be jammed or cut, leaving aircraft to make decisions alone. In such cases, human pilots are still more reliable than machines. While AI can assist and even fly under normal conditions, most military leaders are not yet ready to trust autonomous systems with life-or-death decisions in the chaos of war. The decision to keep a human in the loop is more than just about tradition. It's a calculated move to reduce risks and preserve control during high-stakes missions. While AI is expected to play a growing role in combat, especially in supporting roles like drones or surveillance systems, the F-47 shows that the U.S. military still believes in the value of human judgment, especially in complex, unpredictable environments. Justin Bronk also acknowledged that choosing to keep a human pilot in the F-47 comes with its own set of challenges. It increases costs, demands extensive training, and raises the risk of needing dangerous rescue missions if a pilot is shot down. However, he believes relying entirely on artificial intelligence at this stage would be a gamble the U.S. military can't afford to take. Not yet. That doesn't mean drones are being left behind. The F-47 will fly with robotic teammates known as Collaborative Combat Aircraft, or CCAs. These AI-powered drones will act as support systems, robot wingmen, handling surveillance, defense, or striking targets alongside the manned jet. Still, the F-47 will remain the centerpiece of the mission, suggesting that human fighter pilots will stay in action for at least one more generation. The timing of the F-47 announcement was strategic. It gave President Donald Trump the opportunity to claim credit for launching America's newest and most advanced fighter. Interestingly, Elon Musk, who often criticizes manned aircraft, was reportedly at a Pentagon briefing during the reveal. Although some believe the future of warfare is robotic, the F-47's unveiling makes one thing clear. The age of the human pilot isn't over just yet. The U.S. military is moving forward with a hybrid approach, keeping a person in the cockpit, supported by a growing cast of AI-driven drones. It's a balanced step into the future, mixing proven tactics with cutting-edge tech. This vision of manned fighters working alongside advanced AI isn't just theory, it's already taking shape. Behind the scenes, industry leaders are investing heavily to bring this hybrid future to life, and Boeing is leading the charge. During the Bernstein 41st Annual Strategic Decisions Conference on May 29th, Boeing CEO Kelly Ortberg shared exciting news about the company's major role in developing the F-47 sixth-generation fighter jet for the U.S. Air Force. He explained that Boeing had made the largest internal investment in its history to support this project, showing just how important it is to the company. Ortberg described the win as a major success, especially for Boeing's St. Louis facility, which already handles the production of the F-15 and F-18 fighters. He emphasized that being chosen for the next-generation fighter would help secure the future of that operation for many years. Ortberg stressed that the F-47 program is not only a huge opportunity, but also proof of Boeing's continued strength in defense technology. He mentioned that the company's proposal for the fighter jet was already very advanced in design and development. Even though he couldn't share many technical details, he made it clear that Boeing's team had created a superior and well-prepared product. He also highlighted the positive impact of the program on team morale, saying the win had energized everyone involved. According to Ortberg, the massive investment in the F-47 had paid off, and it clearly showed that Boeing still had the capability to deliver cutting-edge solutions for national defense. The scale of the F-47 program is significant, largely because it is the only sixth-generation fighter the U.S. Air Force plans to adopt. This is a major shift from previous strategies. In the fifth-generation era, the Air Force commissioned both the F-22 and F-35 under a high-low mix strategy, where the F-22 served as the high-end air superiority fighter and the F-35 as the more versatile and affordable option. However, the F-22 program faced several issues, leading to an early end to production and efforts to retire the fleet much earlier than expected. In contrast, during the fourth-generation period, the Air Force operated a broader mix. It used F-15s for high-performance air superiority and F-16s as lighter multi-role fighters. These worked alongside specialized jets like the F-111 and F-117, while the F-20 was developed for export markets. That era showed a strategy of spreading capability across multiple platforms. The decision to now rely on a single sixth-generation fighter, the F-47, is a major departure from tradition. This focus on one platform could become even more significant if the U.S. Navy decides to adopt a version of the F-47 for its own needs, instead of developing a completely new jet through its F-A-20 program. If that happens, it would further increase the scale, funding, and strategic importance of the F-47 project. At this stage, it's still unclear whether the Navy's F/A-XX contract will go to Boeing, which leads the F-47 program, or to rival Northrop Grumman. Lockheed Martin, which led the F-22 and F-35 programs, has already been ruled out. As a result, the outcome of this decision could shape U.S. air power for decades to come. Unlike the F-22 and F-35, which were developed during a period of relative calm after the Soviet Union's collapse, The F-47 is being created in a much more urgent and competitive environment. When the US began working on the F-22 and F-35, there was little global pressure and delays were tolerated. But today, the world is facing rising geopolitical tensions, especially with China making major progress in advanced fighter technology. In December 2024, China revealed flight-ready prototypes for not one, but two separate sixth-generation fighter programs. Since then, both aircraft have gone through intensive flight testing, signaling that China is moving quickly to bring next-generation fighters into service. This rapid pace has added serious pressure on the US to ensure the F-47 is not only developed quickly, but also equipped with the most advanced capabilities possible. China's success in rolling out new generations of fighter jets, along with its ability to deliver fast and meaningful upgrades, has shown that it could outpace the US in this race. A key reason is the scale and efficiency of China's industrial base. Its defense industry can move at high speed and on a large scale, while also putting enormous resources into research and development. Because of this, the F-47 is not just another defense project, it's a response to a fast-moving global threat. The United States can no longer afford delays or outdated systems. Developing the F-47 quickly and getting it into service is essential to staying competitive in the air. The pressure to match or surpass China's pace is now driving a level of urgency and focus that was missing during earlier generations of fighter development. This growing urgency isn't just influencing US defense priorities, it's starting to reshape international partnerships too. As timelines tighten and global threats evolve, allies like Japan are looking for faster, more reliable options to maintain their edge in the skies. Boeing's new F-47 sixth-generation stealth fighter might not just be America's next big leap in air power, it could also be heading to Japan. According to reports, the US President Donald Trump personally pitched the idea of selling a special export version of the F-47 to Japan. He raised this possibility during the public announcement of Boeing's win in the US Air Force's Next Generation Air Dominance program back in March. At the same time, Japan is thinking about buying more F-35 fifth-generation jets to cover any delays in the Global Combat Air Program, due to the growing worries about how long that joint program might take to produce results. The idea of Japan buying the F-47 reportedly came up in a phone call between Trump and Japanese Prime Minister Shigeru Ishiba. According to Japan's Asahi Shimbun newspaper, the call happened unexpectedly and was later confirmed by Ishiba's administration. Interestingly, it took place just days before Japan's chief trade negotiator, Ryosei Akazawa, visited the US to discuss Trump's economic tariffs. During a recent phone call, Donald Trump and Japanese Prime Minister Shigeru Ishiba reportedly discussed strengthening the US-Japan military alliance. Trump brought up the number 47, asking Ishiba if he agreed it was a good number, a reference to the new Boeing F-47 fighter jet and Trump being the 47th US president. Japan is reportedly growing concerned that the Tempest fighter, developed under the Global Combat Air Program, may not be ready in time to meet its defense needs. According to Reuters, two unnamed defense sources say Japan is now exploring options to bridge the gap in its fighter fleet. One source blamed the lack of urgency from Italy and the UK for GCAP's slow progress, while the other pointed to delays in unifying each country's vision for how the future aircraft should operate. Despite these concerns, a spokesperson from the British Ministry of Defense told Reuters that the UK, Italy, and Japan remain focused on delivering a next-generation fighter by 2035. However, at least one British GCAP official has suggested that Tempest may not fully replace the Royal Air Force's Typhoons until the 2040s, later than Japan might prefer. To fill the potential gap, Japan's first fallback option appears to be buying more F-35s. While the GCAP remains Japan's long-term fighter plan, delays may force the country to turn to proven platforms like the F-35 to ensure its air defense remains strong during the transition. A new F-35 purchase could benefit Japan economically. Ryosei Akazawa noted that such a deal could support trade talks with the US, since defense imports would boost the American trade surplus. However, it could also threaten Japan's commitment to GCAP. And if Japan pulls out, the UK and Italy may struggle to continue the program alone. GCAP already faces financial strain due to UK defense budget pressures. An alternative could be the F-47, a sixth-generation stealth fighter recently announced by the U.S. If the U.S. offers the F-47 to Japan, it could give Tokyo faster access to next-generation air power. Trump hinted at potential export sales of the F-47, possibly with downgraded features for allies. Still, its projected price, $180 to $200 million, could be a hurdle. Yet for Japan, it offers a rare chance to fly America's top fighter, something never permitted with the F-22. It would also deepen Japan-U.S. military cooperation, especially important amid rising tensions with China, Russia, and North Korea. Japan's defense needs are growing, and the delay of GCAP might push it toward proven U.S. platforms like the F-35 or even the F-47. However, this comes at the cost of long-term independence. GCAP, led by Mitsubishi Heavy Industries, gives Japan full control over its fighter, including upgrades and exports without U.S. approval. It also ensures industrial and financial benefits from each sale. With threats rising in the region and Japan increasing its military budget, Tokyo may have no choice but to explore faster, more reliable alternatives to ensure its air defenses remain strong. But any decision to shift away from GCAP would have lasting international consequences. The YF-23 is back and better. Once a ghost of aviation history, this stealth fighter vanished after losing to the F-22. But now the United States has shocked the world by unveiling a futuristic version so advanced it's being called a UFO airplane. With alien-like stealth, unmatched speed, and next-generation tech, this reborn YF-23 could change the skies forever. Could this mysterious craft be America's leap into the future of warfare? And is the world ready for it? Join us as we explore the capabilities of the futuristic YF-23 UFO airplane that the U.S. just revealed. Conceived by Northrop in the late 20th century, a time when digital design was barely emerging and budgets constrained ambition, this fighter was a machine built to rewrite the rules of air combat. It was unlike anything the world had seen, and it promised stealth and speed in ways that felt almost otherworldly. If the Air Force had chosen it under the Advanced Tactical Fighter Program in 1990, the very concept of sixth-generation fighters might have arrived decades earlier. Its ideas did not vanish with its official loss to Lockheed's YF-22. Instead, they lingered, quietly influencing the next era of aerial warfare. Long before the YF-23 took shape, Northrop's engineers were already exploring the boundaries of stealth. Beginning in 1981, Robertson, Dusky, and Upinglu envisioned a fighter that could move unseen, agile yet invisible, blending the speed and power of modern jets with the shadow-like presence of a phantom. When American reconnaissance satellites first caught sight of the Soviet Union's Su-27 and MiG-29 fighter prototypes between 1977 and 1979, alarm bells rang loudly across the United States. These sleek Soviet jets promised to erase the combat and maneuverability advantages of America's top fighters, the freshly introduced F-15 Eagle and the agile F-16 Fighting Falcon. The growing Soviet threat did not stop there. In 1978, the USSR unveiled the A-50 Airborne Warning and Control System, a flying radar fortress, along with increasingly sophisticated surface-to-air missile defenses. For the U.S. Air Force, the message was clear. Its tactical edge was being challenged, and the future battlefield would demand something extraordinary. By 1981, the U.S. Air Force responded by laying down requirements for an ambitious new aircraft, the Advanced Tactical Fighter, or ATF. This jet would not simply match the Soviets. It would leap into the future with revolutionary technology. Engineers envisioned a machine built from composite materials and lightweight alloys, powered by advanced engines, guided by digital flight control systems, and cloaked in cutting-edge stealth. It would be versatile, performing both air-to-air duels and precision air-to-ground strikes with equal mastery. When the Air Force released its request for information in May 1981, aerospace companies flooded in with creative concepts. The program, codenamed Senior Sky, was still shaping its identity, so responses varied wildly. Northrop, known for bold ideas, offered 3 designs that ranged from an inexpensive lightweight fighter to a hyper-agile performer to a low-observable missileer. All were compact, emphasizing agility and cost efficiency. One prioritized maneuverability at the cost of stealth, another maximized invisibility but sacrificed agility, and a third struck a careful balance between the two. This final path evolved into a radical design with diamond wings, butterfly tails, and a fuselage sculpted to deflect radar. By 1983, momentum had picked up. The Air Force established the ATF System Program Office at Wright-Patterson Air Force Base, growing from the early concept development team. After close talks with Tactical Air Command and industry leaders, the SPO decided the ATF's heart would lie in air-to-air combat. It would replace the F-15, soar at supersonic speeds, cruise effortlessly above Mach 1, and dance through the skies with unmatched maneuverability. Northrop responded with the N-360, a futuristic Mach 2 plus fighter sporting delta wings, twin-thrust vectoring engines, and bold vertical tail designs. But another secret was reshaping the future: stealth. The SPO had been briefed on classified Black World projects like Have Blue and the F-117 Nighthawk, Tacit Blue, and the advanced technology bomber that later became the B-2 Spirit. These programs showed that radar invisibility was no longer science fiction. The ATF would now need not just speed and agility, but near invisibility. Northrop was uniquely positioned. Since October 1981, a stealth design team led by engineer Robert Sandusky had been quietly experimenting. By 1985, he was joined by Yu-Ping Liu, a B-2 scientist with rare mastery of both radar signatures and aerodynamics. Together, they pushed three daring concepts: the agile, maneuverable fighter, emphasizing aerobatics with minimal stealth; the ultra-stealth fighter, nicknamed the Christmas tree for his sharp, angular planform; and the high-stealth fighter, or HSF, which struck a near-perfect balance. The high-stealth fighter became the crown jewel. With diamond wings, butterfly tails, and carefully aligned surfaces, it absorbed radar waves and slipped past detection. Its nose, nicknamed the platypus for its unique curves, reflected Liu's genius in blending stealth with airflow. By 1985, the HSF had evolved into a design that looked strikingly close to what the world would later recognize as the Northrop YF-23, a sleek predator embodying both invisibility and speed. Every line and surface of the aircraft was purposeful. Its cockpit sat higher than most, giving pilots an extraordinary field of vision, while the peculiar platypus-shaped nose allowed for sharper attack angles. The fuselage was a masterpiece of stealth, sculpted to slice through radar and air alike. Beneath the surface, a tricycle landing gear supported the craft, and a spacious internal weapons bay kept its firepower hidden from prying eyes. Its twin engines were tucked into separate ducts to minimize radar exposure, and their exhaust passed through heat-dissipating tiles made of a porous alloy, masking the aircraft from infrared-guided missiles. Unlike the YF-22, the YF-23 did not need thrust vectoring to turn. It could cruise above Mach 1.5 without afterburners, combining speed, stealth, and survivability in a rare harmony. Testing confirmed it was quieter, faster, and more elusive than its competitor. Flight testing proved that Northrop's predictions about the YF-23's performance were accurate. The aircraft could achieve a maximum angle of attack of 25 degrees and was considered stealthier and faster than the YF-22. Its weapons bay, carefully designed for low radar signature, was tested for acoustics, though it never launched live missiles during trials. Lockheed's YF-22, by comparison, did fire AIM-9 Sidewinders and AIM-120 AMRAAMs, giving it an edge in live demonstration. One of the most intense moments came on November 30th, 1990, when the YF-23's PAV-1 prototype performed a grueling combat demonstration. 6 flights within 10 hours, showing stamina, speed, and reliability. Over the course of the program, the 2 YF-23s flew 50 sorties, logging a total of 65.2 flight hours. Meanwhile, Lockheed's YF-22 completed more flights and more testing hours, which later proved crucial in the Air Force's decision-making. By December 1990, both Lockheed and Northrop had submitted their final evaluations and proposals. Despite outperforming the YF-22 in speed, stealth, and overall capability, the Air Force chose Lockheed's design, prioritizing low-speed agility and other logistical factors. Most aircraft shelved under similar circumstances faded into obscurity, yet the YF-23's story was far from over. Back in the year 2004, Northrop Grumman brought forward an ambitious proposal that drew heavy attention within aviation circles. The company suggested developing an advanced bomber known as the FB-23, nicknamed the Rapid Theater Attack, or RTA. It was intended to meet a United States Air Force call for an interim regional bomber. It was set to compete against other strong contenders, including the Lockheed Martin FB-22 and Boeing's modified B-1R concept. Unlike its fighter predecessor, this proposed bomber would feature a two-seat cockpit and a much larger overall structure. While maintaining a similar planform shape to the original F-23, the FB-23 would be considerably bigger in every dimension. Its length would stretch to around 100 feet, making it capable of carrying heavier payloads and traveling greater distances to match the role of a true tactical bomber. The envisioned aircraft would boast an impressive combat radius of over 1,600 nautical miles, equal to nearly 1,840 standard miles, or almost 2,960 kilometers. Alongside this range, it was expected to carry an internal payload of up to 10,000 pounds of ordnance. To support these needs, the FB-23 would rely on powerful engines equipped with round axis emimetric nozzles positioned above the aft deck. This was a departure from the YF-23 fighter, which had used wedge-shaped flaps on its nozzles. Despite the changes, Northrop Grumman retained certain trademark features, such as the semicircular inlet design paired with a conical compression bump, which had been a hallmark of the original prototype. To push the project further, the company even modified the YF-23P AV-2 prototype, turning it into a display model that could demonstrate how the proposed bomber might look and operate. Aviation enthusiasts and defense officials were intrigued by the concept, yet the FB-23 faced an uphill battle. In 2006, the Quadrennial Defense Review effectively ended any hope for the project. The review concluded that the United States Air Force should pursue a long-range strategic bomber rather than settle for a regional interim design. As a result, the FB-23 proposal was shelved in favor of programs that eventually evolved into the next-generation bomber and later the long-range strike bomber effort, which produced the B-21 Raider. But that did not discourage Northrop Grumman, because years later, in 2018, Northrop Grumman once again explored possibilities for resurrecting aspects of the F-23 design. This time, the interest came from abroad. The Japan Air Self-Defense Force released a request for industry partners to help develop its next-generation fighter, often referred to as the FX, bridging both 5th and 6th generation capabilities. Speculation quickly rose that Northrop Grumman might pitch a modernized version of the F-23 to Japan as a potential solution. Meanwhile, Lockheed Martin responded with a proposal based on a modified F-22 airframe. However, both American options ultimately failed to win Japan's approval, primarily because of concerns tied to cost in industrial workshare agreements. Everyone must have thought that the YF-23 had no future in aviation, but the story did not end with that loss. Its design philosophies re-emerged decades later, influencing the most advanced aircraft of the 21st century. The B-21 Raider adopted hidden engines, recessed nozzles, and minimized thermal signatures, perfecting ideas that were initially tested in the YF-23. But that's not all. Similarly, 6th-generation fighter programs around the world, including the Global Combat Air Program, adopted its radical approach: smooth silhouettes, blended wings, concealed intakes, and a philosophy that prioritizes invisibility and rapid strike over traditional dogfighting. Its revolutionary concepts also re-emerged as the backbone of the next-generation air dominance program. Features that once seemed fantastical, keyless design, blended wings, exotic air intakes, hidden engines, no vertical tails, and a smooth thermal profile, are now shaping the fighters of tomorrow. Boeing's F-47 concept, for instance, mirrors the YF-23's silhouette so closely that Darrell B. Cummings, one of the original engineers, described it as a continuation of his team's work from 30 years prior. What seemed over-engineered in the 1980s and 90s is now recognized as foresight. At the time, flight control systems could not stabilize an aircraft without vertical fins, and nozzle heat shielding was experimental, often yielding unpredictable outcomes. Today, with high-speed processors, autonomous stabilization, and advanced airflow simulations, those once risky ideas have become reliable, foundational elements of modern stealth aircraft design. The philosophy behind the YF-23 remains as relevant as ever. Rather than dogfighting, it focused on first look, first shot, and first kill. Its innovations live on in aircraft like the B-21 Raider, whose hidden engines, recessed nozzles, and low thermal signature directly reflect lessons learned from the YF-23. In a modern battlefield shaped by hypersonic weapons, autonomous drones, and integrated sensor networks, invisibility and speed are survival, and the YF-23 set the standard. At the heart of its enduring influence lies stealth as a fundamental principle. The YF-23's engines were tucked deep within the fuselage, exhaust flows cooled through heat-absorbing tiles, and radar-deflecting surfaces made the aircraft almost invisible to sensors. This was not merely camouflage, it was a philosophy of survival. Modern jets like the B-21 Raider owe much to these ideas, adopting deeply recessed engines, hidden nozzles, and shielded intakes to minimize thermal signatures. Engineers confirmed that the Raider did not simply borrow concepts, it perfected them, translating early experimentation into practical, battle-ready solutions. But stealth alone does not define these aircraft. Digital intelligence has become equally crucial. The Raider integrates virtual modeling, digital twins, and modular systems, transforming the fighter into a flexible, adaptive platform. The YF-23 envisioned a world where pilots operate not as isolated warriors, but as central nodes in a larger network, commanding automated systems, drones, and integrated sensors. What was once experimental guesswork in the 1980s is now reliable engineering, allowing aircraft to vanish from sight while delivering precision strikes. The ripple effect of the YF-23 extends beyond the United States. Allies, including Britain, Japan, and Italy, collaborate on the Global Combat Air Program to develop sixth-generation fighters. Their designs show Northrop's radical innovations: smooth, flowing surfaces, concealed propulsion systems, no vertical tails, and highly aerodynamic silhouettes. AI co-pilots, automated threat detection, and fully digital cockpits make these aircraft more than machines. They are extensions of a networked battlefield where speed, invisibility, and intelligence determine survival. Today, with hypersonic weapons, multispectral sensors, and autonomous drones shaping combat, its vision is prophetic. Every curve, every intake, every hidden line on modern stealth aircraft reflects lessons first explored on the YF-23. Though it never flew in production, its legacy endures, influencing aircraft that dominate skies and redefine aerial supremacy. While critics initially called it too radical, today its design principles are echoed in cutting-edge programs across the globe, proving that visionary ideas never truly fade. The evolution of aerial combat has shifted the very role of the pilot. Modern sixth-generation jets are designed around artificial intelligence, where human pilots are no longer lone combatants, but commanders of interconnected digital armies. AI co-pilots anticipate threats in fractions of a second, automated systems detect dangers faster than any human reaction, and fully digital cockpits transform the pilot into the brain of a vast airborne network. Decades ago, the YF-23 hinted at this paradigm shift. Its geometry, once considered unconventional, was a blueprint for a future where speed, invisibility, and first strike capability outweighed traditional dogfighting agility. It is essential to dispel a long-standing myth. The YF-23 was not inferior to Lockheed's YF-22 in performance. Both aircraft were extraordinary, but Northrop pursued a philosophy focused on survivability and lethal efficiency. Their principle was simple yet devastating: first see, first strike, first kill. No endless circles, no cinematic duels, just the clean, ruthless logic of modern warfare. In today's era of hypersonic missiles, multispectral sensors, and autonomous drones, this philosophy has proven prescient. guiding the development of platforms that dominate the skies not through agility alone, but through unseen mastery. International programs like the Global Combat Air Program, alongside America's next-generation air dominance initiatives, continue to draw from the YF-23's DNA. Blended wings, smooth thermal profiles, and buried engines are no longer experimental. They are foundational. The B-21 Raider, often seen as a successor to the B-2 Spirit, perfected many concepts first tested in the Black Widow II, including heat suppression, recessed propulsion, and low observable design. Stealth is no longer optional. It is the essence of survival. The battlefield of today is no longer defined by dogfights or simple air-to-air duels. It is a complex, fast-moving arena dominated by hypersonic weapons capable of crossing continents in mere minutes. Sensors now operate across multiple spectra, radar, infrared, and electronic frequencies, allowing military forces to detect threats long before they appear on traditional systems. Autonomous drone swarms fly alongside manned aircraft, overwhelming defenses not through brute force alone, but through intelligence, numbers, and relentless coordination. At the heart of this high-tech warfare is real-time sensor fusion, connecting satellites, jets, and command centers into one massive digital brain, orchestrating battles with a precision that would have seemed unimaginable decades ago. In this environment, maneuverability, once the hallmark of fighter superiority, has become secondary. True survivability comes from invisibility, from the ability to remain unseen until the decisive moment. This is where the legacy of the YF-23 becomes strikingly relevant. Although the YF-23 never entered production, its design philosophy has shaped the most advanced fighter programs in the world. The aircraft was conceived not for Hollywood-style dogfights, but for the future of warfare, an era defined by striking first, striking unseen, and striking with lethal efficiency. The next-generation air dominance program, the B-21 Raider, and international initiatives like the Global Combat Air Program may appear different on the surface, yet they share the same core principles first pioneered by the YF-23. These aircraft are not merely fighters, they are instruments of air dominance designed to control the battlefield through stealth, speed, and integrated intelligence. Every curve, every hidden intake, and every recessed engine in these modern platforms echoes the visionary thinking of Northrop engineers who, decades ago, imagined a plane from the future. In the sixth-generation era, the mission is no longer to outmaneuver the enemy in the sky. It is to vanish from detection, to deliver strikes before adversaries even know they are under threat. The YF-23 anticipated this reality long before the technology to realize it existed. Its advanced aerodynamics, hidden exhausts, and sleek, radar-resistant design were early blueprints for today's stealth-first philosophy. The aircraft's spirit endures, influencing the architecture of modern jets that integrate artificial intelligence, autonomous systems, and digital command networks. What was once dismissed as radical, over-engineered, or ahead of its time has proven to be prophetic. The YF-23 was more than a prototype. It was a thinking model, a design philosophy that whispers through the silhouettes of every next-generation fighter. Thanks for watching. Before you go, click the link on your screen to check out another video. See you there.